Okay, can you see the slide? Our today's topics is the kinematic modeling of manipulator arms. Last week we performed some derivation for the mathematical tools to represent reference frame in the terms of the metrics. We introduced the rotational metric and the homogeneous transform, and we still didn't know how can we apply the concept of the rotational metric and the homogeneous transform to the manipulator application. So today we will review the concept of the open kinematic chains manipulator. It will be similar to the introduction from our last week, but the new topics for today is how to assign frame on a robotic link by using the Denavit-Hartenberg notation. We mentioned that the robotics arm has the physical link, but we will try to attach frame, the ideal frame on the robot link. And in order to explain the robot motion, we explain the motion of the frame, the relative position, the relative velocity, the relative acceleration, and the orientation of the frame, instead of talking about the physical link of the robot. But there are different methods. There are few different methods to attach frame to the robot. But the way that we are going to do, we call the Denavit-Hartenberg convention. They will talk about the steps we need to do to attach frame to the robotic link. And after we attach the frame with this convention, we can find the parameter of the robot link. Today we will introduce what are the parameters that can represent each robot link, and how can we identify the parameter of the robot link. And of course, the parameter will represent one robot link, and from the parameter we can compose the homogeneous transform. Today we will have a short review for the homogeneous transform. Actually, last week we spent time to derive the homogeneous transform. We know how can we compose the homogeneous transform from the rotational metric and the position of the frame origin. Today we just only have a short review for the homogeneous transform, but we will see what is the benefit of the homogeneous transform. How can one metric of the homogeneous transform can be composed from the parameter of the robot link that represent that robot link. And we know that the homogeneous transform, we know that the homogeneous transform can be written in the terms of the product of multiple metrics, so that we can get the relationship between the link, the frame of the robot For example, if the robot has the global frame 0 and has the frame on the link 3 as the frame 3, if we obtain the homogeneous transform of the link 1 with respect to the frame, the global frame 0, if we obtain the homogeneous transform of the link number 2 with respect to the link number 1 and obtain the homogeneous transform of the final link with respect to the link 2, if we compute the product of the metric of the homogeneous transform, finally we can relate the end effector, the final link, to the global reference, and by attaching the frame to the link, we can obtain the parameter. With the parameter will be the link length, link offset, link width, and link angle, the joint angle. Today we will learn how to find these 4 parameters that represent one link, and the 4 parameters can compose one metric. And this metric 4x4 is this one. Is one homogeneous transform to represent that link of the robot. If your robot has n link, you just multiply the n metric of the homogeneous transform, and you can get the final relationship between the n link and the global frame. This method will help us to find the forward kinematic of the robot. You know that the homogeneous transform is 4x4 metric. If you have n metric of the 4x4 metric, and you obtain the product of the product of the homogeneous transform of the link n with respect to the frame 0 will be a metric 4x4 also. And this metric is a homogeneous transform. We know that the 9 component in the homogeneous transform, the 9 component here will represent the rotational metric, of the frame n with respect to the frame 0. And we still have the 3 components that are the position vector, and we have 0, 0, 0, and 1 in the 4x4 metric. And this position vector is a P of the origin of the frame n with respect to the frame O. P of the n origin with respect to the frame O. So the meaning of the forward kinematic is, if we know the joint variable, for example, if we know theta 1, theta 2, theta 3 until theta n, if we know the joint variable, what is the Cartesian coordinate that correspond to the joint variable? What is the position in x direction, position in y direction, and position in z direction in the Cartesian coordinate that correspond to the joint variable? And what are the orientation? And the orientation is represented by the rotational metric. So the parameter of the link, we have 4 parameters for each link, but the link length, the link to width are the link parameter that are the constant and never change. The offset sometimes can be constant for the level root joint, but if we are talking about the prismatic joint, sometimes the offset of the prismatic joint is the value that we can control by actuator, by linear actuator. For the joint angle, if the joint is the level root joint, the joint angle can be controlled by rotational actuator. So maybe for the input of the system in the joint variable, it can be the theta for revolute joint, or it can be the D for the prismatic joint, and we can obtain the position. It seems like if we know that if joint A rotates by theta 1 degree, maybe joint 2 is a linear actuator and it translates with the offset D2. If the joint 3 is the level root joint, we can obtain the final position at the end point. This is the goal for our today class. Okay, to review the idea of the open kinematic chain, the manipulator arm that we study in our today class, in our class, industrial robot class, mainly are the manipulator that can be modeled by an open chain of link. Open chain of link, it means we begin from the link 1, link 2, and until the link end. And the links are connected with each other by joint. You can see that the base frame is link 0. The base frame is link 0. Link 0 is connected with the link 1 by a joint 1. Link 1 is connected to link 2 by a joint 2. So the link is connected. The links are connected with the neighbor link by the joint. And our idea is we're gonna attach the frame on each link on the manipulator arms. In this picture, you may see that for the base frame or link 0, they attach the frame 0. They attach the frame 0. The frame 0 has the origin O0 and has the x-axis x, y, z, 0. The link 1 also, we attach the frame 1. The link 2, we attach the frame 2 on the robot link. But today, we will learn how to attach the frame to the link. What should be the position? What should be the position of the frame origin? And what should be the orientation of the frame? Which means the X, the Y, the Z direction of the frame. What should be the direction of the X, Y, Z direction of the frame? Of course, we can attach frame to the link in many possible ways. We can put origin of the frame somewhere on the robot. We can put it on the center of mass, or we can put it on the joint, we can select the direction of the Z direction in any direction, arbitrary direction, but by the Denavit-Hartenberg notation. To follow the Denavit-Hartenberg notation, we have only few possible way to attach frame on the robot. And if we appropriately attach the frame by the Denavit-Hartenberg notation, we can obtain the corresponding DH parameter, the link length, link offset, link to width, and the joint angle that correspond to the frame. And from these 4 parameters, yes, we can compose the homogeneous transform of that link, the 4x4 matrix of the homogeneous transform of that link. And the homogeneous transform will relate just only the frame. For example, the homogeneous transform of this link will relate the link number 2 to the link number 1. And we have the homogeneous transform that relate the link number 3 to the link number 2, like this. And when we obtain the product of the homogeneous transform, we can find the forward kinematic. But here, the homogeneous transform will relate the frame. And it can describe the position and the orientation of that frame with respect to the previous frame and also with respect to the base frame. And the meaning of the forward kinematic is, hey, if we know the joint angles, if we know the theta 1, theta 2 until theta n, or sometimes it may be the offset 1, offset 2. If we know the joint angle, if we know the joint displacement, what is the position of the end effector at the link end with respect to the base frame? The joint, when we talk about joint, joint form connection between a pair of link. Joint form connection between a pair of link. What does it mean? It means that there will have a 2 surface sliding over another to create relative motion between a pair of body. Let's check the levolute joint here. The levolute joint. The levolute joint will have the first part that have a pin, right? Have a pin. And this pin is put into a hole of the second part. The pin is put into the hole of the second part. Of course, at the surface of the pin, for the pin, the external surface of the pin, for the hole, the internal surface of the hole, will have the surface that's sliding over one another and have the relative motion. In our class, the joint for the robot manipulator, that we are considered in this class, each joint will have only 1 degree of freedom. Each joint will have only 1 degree of freedom. What does it mean? In general, for the mechanical application, we have various types of joint, but the 1 degree of freedom joint that we mainly consider for the industrial robot are only the level joint and the prismatic joint. The level joint provide the rotation about the axis of the rotation and have 1 degree of freedom. The theta is 1 degree of freedom of the level joint. And for the prismatic joint, if you see here, the collar can be moved upward and downward against the shaft, or you can think in the opposite way. The shaft inside, the rod inside can be moved upward and downward with respect to the collar, the rod and the collar. The prismatic joint have only 1 degree of freedom. And please be aware, for the prismatic joint, it cannot be rotated. If you see in this picture, there is this part to prevent the rotation. For prismatic joint, we can only move it along the axial direction of the joint, and it cannot be rotated. Based on your experience, of course, I think you may have some experience with building some mechanism that use cylindrical joint. The cylindrical joint, you can move it upward and downward. In the same time, you can rotate it about the axis of the rotation. The cylindrical joint has 2 degrees of freedom. Of course, in some industrial robot, we may have the cylindrical joint in the robot. But in order to analyze the kinematic of that robot, you should separate the degree of freedom of that joint to be 2 mathematical joints. The cylindrical robot is 1 mechanical joint or 1 physical joint. But by our method, we study in this class the method to analyze the kinematics of industrial robot. You should separate the joint to be 1 degree of freedom per each joint. So the cylindrical joint consists of 1 level root and 1 prismatic joint, 1 rotational and 1 sliding. We cannot combine it. What is the screw? The screw can also have the linear motion. In the same time, the screw can perform like level root joint also. How many degrees of freedom of the screw joint? Trywit, are you here? Okay.
Yes ครับอยู่ครับ
Trywit, how many degrees of freedom of the screw joint?
1 นะครับ
Okay.
2 เหรออาจารย์
Okay, the screw joint we can rotate with the theta, and we also can see the displacement in the vertical direction. It seems like we have 2 possible ways of motion in the screw joint. By the way, we don't have the freedom between these 2 degrees. These 2 degrees are constrained by the thread of the screw. If you rotate by the theta angle, you cannot select the displacement or the offset. If you rotate it by theta, the constraint of the screw will force you to move with a corresponding displacement. So the screw joint has only 1 degree of freedom.
โอเคครับ
How about the planar motion? The motion of a block on plane. How many degrees of freedom of the box moving on a plane? Of course, the center of the gravity or the center of mass or one reference point of the box the OB or the origin of the frame of the box can be described by the position X and Y with respect to the global frame. And the box can rotate. The box can rotate with the angle with respect to the direction of the global frame. So you need 3 degrees of freedom to indicate the position and the orientation of the box on a plane. So the planar joint can allow 3 degrees of freedom. It can move position on the plane, XY position. We have 2 degrees of freedom for the motion. And we have 1 additional orientation degree of freedom. So for a planar joint, we have 3 degrees of freedom. How about a spherical joint? A spherical joint, we have a circle, we have a sphere inside, and we have a cup outside. For a spherical joint, we know that the X, the Y, the Z direction of the reference frame that attached to the moving part, the X, Y, Z position cannot be moved. The spherical joint constrain the motion, constrain the translation in X, Y, Z direction. We cannot move it, but we can still rotate. You can rotate the spherical joint about the x-axis. If you rotate the spherical joint about the x-axis, it can be rotated in this direction. You also can rotate the spherical joint about the y-axis. You also can rotate the spherical joint about the z-axis. So the spherical joint has 3 degrees of freedom. The rotation about the x-axis, the rotation about the y-axis, rotation about the z-axis. but the position are constrained, are fixed, and cannot be moved. Okay, the with Hartenberg notation. The idea is when you have a robot, and have a link on a robot, the link that doesn't move, this one is fixed to the floor and cannot be moved. We call link 0. The immobile base is link 0. The first moving rigid body is link 1. The second moving rigid body is link 2. And of course, we have the connection until the link end. How about the joint? The joint I connect link I-1 and link I. The joint I connects link I-1 and link I. This is the joint that connect link 0 and link 1. This is joint 1. How about the joint that connect link 2 and link 1? This is joint 2. This is easy to understand. This is the first joint that can be rotated. It's joint 1. This is joint 2. We don't have joint 0. We need to find the physical joint, so we cannot find the joint 0. We begin from joint 1. For the link, it also makes sense that the link 1 is the first link that's moving. Link 2 is the second link that's moving. The link 0 cannot be moved. We not count it. If we see the picture, the schematic here is easy to understand because it's on the 2D plane. But if we draw a structure in 3D, it will increase the complexity, but the idea is still the same. Joint I provide the connection between the link I-1 and link I. If this is an immobile base, if this is link 0, if this is link 1, of course this is gonna be joint 1. If this is joint 1, this is joint 2. No, if this is link 1 and link 2, the joint gonna be joint 2 that connect between the first link and the second link. The link parameter is the parameter that describe the link. The ring parameters are the parameter that describe the link. What are the parameters that describe the link? The key for this, the first parameter we are talking about is the length of the link. if you build a robot, maybe you are building this part, the length of the link sometimes don't need to be the direction from here to here. Sometimes it don't need to be the direction from here to here. In order to find the length of the link, you need to find the mutual perpendicular line that connect the joint axis I and I plus 1. For example, if you want to find the length of the link 1, the link I, if you want to find the length of the link I, you need to draw the axis of the joint I, the axis of rotation of the joint I. You need to draw the axis of rotation of the joint I plus 1. And then you need to find the mutual perpendicular line. What is the meaning of the mutual perpendicular line? You should find a line that have the perpendicular angle with the joint I and also perpendicular to the joint I plus 1. You should find this line. And the length of this line will be link length. If we go back to the 2D picture, the axis of rotation of joint 1, the axis of rotation of joint 1 may be in this direction, point out from the paper. This line is point outward from the screen. The joint 2 also has the axis of the rotation point outward from the screen. So in this case, what is the mutual perpendicular line? If these two lines are parallel, point outward the screen in the same direction, the mutual perpendicular line can be this line or this line or anywhere, because the two lines, the two axes of joint 1 and axis of joint 2. If the axes of the joint are parallel, the mutual perpendicular line are infinite line. But what are the length of the line? If the direction from here to here is L1, if the direction from here to here is L1, the link length will equal to L1 if you have the parallel axis. But if the two lines are on the different plane, for example, if you have one line going upward and you have another line that point out from the screen, you're gonna have only one line that provide the perpendicular, that be the mutual perpendicular line. If the line are on the different plane, you can find only one mutual. If the line are on the different plane, you can find only one line. And the length of this line gonna be the link length. How about the link twist? The link length consider the distance between the joint axis along the mutual perpendicular line. The link twist consider the direction difference between the axis. In this picture, the joint I is point in this line. The joint I plus 1 have some angle with the joint I. The angle between joint I and joint I plus 1, if we draw a line that parallel to joint I here, you can see that we have one angle different here, between the joint I and I plus 1. This angle we call link twist. How can we, of course we can know the angle, the magnitude of the angle of the link twist, but how can we find the direction, the sign, positive or negative? The idea is we need to use the right hand rule. It means you need to use your thumb in the direction of the mutual perpendicular. You need to use the thumb in the direction of the mutual perpendicular that connect link I, connect joint I to joint I plus 1. The mutual perpendicular that connect joint I to joint I plus 1 is this line, and the direction is point in this direction. The mutual perpendicular is point in this direction. To obtain the link twist, you need to use your thumb to point to the direction of the mutual perpendicular, and then use your forefinger to the direction of the joint I, upward in the direction of the joint I. Then rotate your finger to the direction of I minus 1. No, I plus 1. From the joint I in the direction upward. From the joint I in the direction upward to the direction of joint I plus 1. You will have this angle by the right hand sense, and this angle we call link twist alpha I. Link twist alpha I. Come back to see, in the simple case, in the 2D case, if we consider the link 1, the direction of the joint axis, joint 1, is go outward from the screen. Joint 2 also point outward from the screen. What is the link twist of the link 1? What is the link twist of the link 1 by the definition? Gavi Tip, are you still here? Gavi Tip, are you still here? Oh no, I'm so sad. I need one volunteer to answer this question. What is the link twist of the link 1?
What's the question นะครับ
The question is, what is the link twist or the alpha of the link 1? The link twist is the angle between the joint I and joint I plus 1. The link twist is the angle between the direction of joint I and joint 1. And my question is, what is the link twist of the link 1? The direction of the joint 1 is this direction, outward from the screen. The direction of the joint 2 is also point outward from the screen. And the joints are pointing into the same direction. So what is the link twist? Okay, if the joint I and joint I plus 1 have different direction, we can find the value of the link twist by using the right hand rule to obtain the angle between the joint axis of the joint 1, joint I and joint I plus 1. But if joint I and joint I plus 1 are pointing into the same direction, it has no angle difference. So the answer is the link twist will be 0 if joint I and joint I plus 1 point into the same direction. And in this picture, the joint axis of the joint 1 and the joint axis of the joint 2 are in the same direction. So the link twist will be 0. In this page, there are two parameters of the link. The two parameters of the link never change. No matter the link will rotate about the joint in which angle. The property, the parameter, link length and link twist never change. If we come back to the 2D picture, no matter this link are here, or when it rotates to different position, different angle, the link length that connect between the joint 1 and joint 2 still be the same, L1. The link twist, which is the angle between this axis and this joint axis, the axis always parallel, and the link twist always be 0. So the link twist and link length never change with the angle of the link. So the link parameter always constant in that link. But for the joint parameter, sometimes it's not constant. Depending on the joint position. The first parameter is the link offset. The link offset means if link I and link I minus 1 share the common axis, or share the joint I. The link offset means what is the distance between the link I and the link I minus 1. Along the common axis. The link I is the mutual perpendicular between the joint I and joint I plus 1. This is the link I. The link I minus 1 is the mutual perpendicular between the joint I minus 1 and the joint I, the mutual perpendicular. The link offset is the distance between this line and this line along the joint axis. It means the link offset is this distance. We come back to the simple case when the robot arm is on a plane. When the robot arm is on a plane, the link 1 is on a plane. The link 2 is also on a plane. And the mutual perpendicular that we consider is on the plane. If we don't have the distance between the mutual perpendicular along the direction of the joint axis, the joint offset will be 0. If you have the link on a plane and the same link, another link on a plane, and of course the two links don't have the distance in the vertical direction, the link offset will be 0. But if the second link is somewhere far from the plane, if the second link is somewhere far from the plane, the offset is measured along the z-axis or the axis of the rotation. The offset. Another joint parameter is joint angle. Joint angle is the angle between the direction of the mutual perpendicular. The mutual perpendicular of the link I minus 1 is point into this direction. And the mutual perpendicular of the link I is point into this direction. If we draw the parallel line here, the angle that measure from the direction of the I minus 1 to the direction of the xi, or the direction of the mutual perpendicular of the link I, the angle here is the joint angle. By using the right hand rule, the thumb going on the upward direction and have the forefinger here, and you rotate from the direction of the I minus 1, the link I minus 1, to the direction of the link I, you can find the joint angle. And you need to apply the right hand rule at the position, at the direction of the joint I. So this meaning, if we consider on the 2D, we have the mutual perpendicular here. We have another mutual perpendicular here. And the joint axis is this direction. So the direction of the first mutual perpendicular is point in this direction. And the direction of this mutual perpendicular is point into that direction. So the joint angle is rotated about the joint axis. With the right hand sense, this is the joint angle. So on the 2D plane, it's easy to understand. But for the 3D motion, we need to consider the direction of the vector. The mutual perpendicular of the link I minus 1 and the mutual perpendicular of the link I, and find the angle, the joint angle. Before this, in these two slides, we intro the 4 parameters describing a link of robot. Without talking about the frame that we attach on the link, we just introduce the physical meaning of the link length, link width, offset, and the joint angle. But as we mentioned in the beginning of the class, in our process, we need to attach frame to our robot and then derive this parameter with respect to that frame. So from here, we will learn the step how to attach frame on a robot. How to attach frame on a robot. The idea, before we see a complicated robot, the first thing we need to do is we draw the axis of all the joint on the robot. We draw the axis of the joint of all the joint on the robot, and the z-axis will be the direction of the joint axis. The z-axis will be the direction of the joint axis, but the number of the frame will be one step less than the number of the joint. For example, if this is joint I, the z-axis will be ci minus 1. If this is joint I plus 1, the z-axis will be ci. The number of the frame will be one step less than the order of the joint, which means if we see our picture, we have the joint 1. We have the joint 1 here, right? And the direction of the joint 1 is point outward from the screen. The axis of joint 1 is point outward from the screen. So the z direction is also in the same direction. with the joint axis, but the number will be one step less than the joint number. So this will be the direction of Z0. This will be the direction of C1 at the joint 2. For the base frame, the base frame is the frame 0. We can set origin anywhere on Z0, but anywhere mean anywhere that make author parameter, length, offset, twist, and angle become 0 as much as possible. You have many ways to select the origin. You have many ways to select the origin along the Z0 axis. For example, if this is Z0, you can put the origin of the frame 0 anywhere on the axis of the Z0, but you should put it on the place that it makes this parameter become 0, so that we can reduce the complication in the metric computation. You may still cannot get an idea from this page, but when we see the simple example, we will return to the step 1, 2, 3 again. How can we apply the step to one robot? For the base frame, we set the origin O0 somewhere on the Z0. On another plane, on another frame, that is not the base frame. We need to set the origin of the frame where the mutual perpendicular intersect the joint axis, which means if we see the mutual perpendicular between the Zi and Zi minus 1, the joint I plus 1, the Z axis is Zi. The joint I, the Z axis is the Zi minus 1. The mutual perpendicular between the joint axis is this line. The origin of frame I need to be the place that the mutual perpendicular intersect with the joint axis. So it means at this point, you need to put the origin of the frame. The mutual perpendicular will be the x-axis, and the position that the x-axis intersect with the z-axis will be the origin of that frame. For here, this is the mutual perpendicular. The mutual perpendicular between the Ci minus 1 and Ci minus 2. The mutual perpendicular between the Ci minus 2 and Ci minus 1. The point that the mutual perpendicular intersect with the Ci minus 1 will be the origin of the frame. Will be the origin of the frame I minus 1. The x-axis is the direction of the mutual perpendicular between the Ci minus 1 and the Ci, and the x-axis need to pass through the origin. So the x-axis is the direction of the mutual perpendicular here, and it needs to pass through the origin. The y-axis is nothing important, we just obtain the y-axis direction from the right-hand rule. Because before this, we know the x direction and we know the z direction, which are the direction of the triangle. X-axis will be the direction of the mutual perpendicular. For the y-axis, we just need to use the right-hand rule. So what is the benefit of the y-axis? If you draw a picture of robot on a plane like this, if you draw a picture of a robot on plane like this, and maybe you know that the x-axis will go in this direction. And you want to say that the z-axis is point outward from the screen. But you don't want to write something complicated like this. Only one way you can do is to write the y-axis that perpendicular to the x-axis. And you will automatically know that the z-axis is point outward from the plane, and you don't need to draw the z-axis. This is only one advantage of drawing the y-axis of the frame on a paper. Before this, we know the meaning of the link parameter and the joint parameter. And we just know the step, how to define, how to attach frame on each link. But when we describe the parameter, we didn't talk about the frame. We didn't talk about the frame. But in our real process, when we analyze the problem, the first step we need to do is we're gonna attach the frame and then derive the parameter. So if we attach the frame first, how can we know the value of this parameter? By this definition, but instead of consider it from the physical meaning, how can we know the value of this parameter from the frame attachment? The link length, we know that the link length is the distance of the mutual perpendicular. We know that the link length is the distance of the mutual perpendicular. So it's the distance between the zi minus 1 axis and the zi axis along the xi axis. The link length is measured along the xi axis and is the distance between ci minus 1 and ci. If we attach the frame first and we need to derive the link length, we can do in this way. The link twist is the angle difference between the ci minus 1 and the ci. The link twist is the angle difference between the ci minus 1 and the ci about the x-axis, which means you need to use your thumb to the x-axis and use your forefinger along the direction of the ci minus 1, the direction of the ci minus 1, and then rotate your finger to the direction of the ci, from ci minus 1 to the ci, and then you get the angle. The thumb needs to point in the x direction, xi direction. For the link offset, Link offset is the distance measured from the position of the origin of the frame I-1 to the x-axis, here. Direction from this point to the x-axis, and measure along the C I-1 axis. Along this axis, the C I-1. The joint angle is the angle difference between the direction of x and direction of xi. The joint angle is the angle difference between the x I-1 and xi about the C I-1 axis. This is the 5 step how to attach frame on a robot. And with this example, we're gonna carefully describe the 5 steps with this example in order to know how to attach frame to a robot. And this robot is a 3-level root joint robot. A 3-level root joint robot. We have first joint here to rotate the robot about the vertical axis. The second joint, the function of the second joint is to lift up, to drive the theta tool to lift up this arm from the floor. The function of the third joint is to create the theta 3. This is the function of the third joint. And how can we attach the frame to the robot? How can we attach the frame to the robot? Before we attaching the frame, one good recommendation is, hey, instead of writing the robot in the home position like this, let's try to redraw the robot in the posture that we can see the angle. Let's draw the robot in the posture that we can see the value of the angle. So the first step we need to do when we see the robot, what is the first step we need to do when we see the robot? We draw the joint axis. We draw the joint axis. And when we draw the joint axis, we can know the Z axis. For the joint 1, we can get the Z0. For the joint 2, we can see the Z axis 1. Joint 3, we see this. So let's see. The step 1. We know that the joint axis of the level root joint is this direction. The joint axis of the level root joint is this direction and this direction. And the robot has only 3 joints, so we draw this. And of course, for the joint 1, for the joint 2, and the joint 3, the Z axis will be Z0, Z1, and Z2. This is the first step, only this. How about the second step? We need to set the origin of the base frame somewhere on the C0 that make most of the parameter become 0. So if you see this, hey, you have the C0 here. It means that you can put origin anywhere on the C0. But what should be, where should be the appropriate position to put the origin? It should be the point that make author parameter for the first link become 0. If you put it here, if you put it here, if you put O0 here, it will be on the same level at the joint exit 1, at the joint exit 2, at the C1. It will be on the same level. The advantage of putting this on the same level is that the offset will be 0. The offset is the distance between O0 and X1 along the C0 axis. Offset is the distance between the origin and the offset is the distance between the origin and the perpendicular along the C axis. So here the offset is the distance measured from the O I-1 to Xi along C I-1 axis. Which means the joint offset 1 is the distance from the origin 0 to the x-axis 1 along the C 0. So if you see this picture again, what? The offset of the link 1 will be the direction from O0 to the X1 along the C0. If you put the origin of the frame 0 here, the offset will be 0. But if you put the origin of the frame 0 somewhere beneath this position, the D will not be 0. And it will increase the complication in our process. So yeah, you select the O0 at the point in the same level with the X1. So you put it here. That was the step 2. How about the step 3? The step 3 is to put the origin of the author frames. We already put the Z of on the frame. We already find the O0. How about the origin of the author frames? Origin of the author frame is the position where the mutual perpendicular between Zi and Zi minus 1, which means the xi, the direction of xi is the direction of the mutual perpendicular between the Zi and Zi minus 1, intersect with the Zi. So if we come back to this picture, the direction from the Ci to Ci, the mutual perpendicular between the Ci minus 1 and the Ci intersect with the joint, the Ci. Okay, the definition. Okay, again, the origin of the frame, which is not the base frame, is the position where the mutual perpendicular between the Ci and Ci minus 1 intersect with the Ci. Okay, so origin of any frame will be the position that the mutual perpendicular between the Ci minus 1 and Ci intersect with Ci. So if we want to find the origin of the frame 1, the origin of the frame 1 should be the intersection point between the line that is the mutual perpendicular between the Z0 and Z1 and intersect with Z1. So what is the mutual perpendicular between Z0 and Z1? What is the mutual perpendicular between Z0 and Z1? Of course, it's gonna be this line that perpendicular to the Z0 and perpendicular to the Z1. And this line will be intersect to the Z1 at this point. So at this point, it's gonna be the origin of the frame 1. It's gonna be the origin of the frame 1. And the direction of the mutual perpendicular, the definition of this, it will be the direction of xi. It will be the direction of xi by the step 4. Xi is the direction of the mutual perpendicular between Zi minus 1 and Zi, and it needs to pass through the origin of the frame. So the mutual perpendicular is here, and it passed through the origin. So this is the x1. How about the O2? How about the O2? O2 should be the line that connect between the mutual perpendicular between C1 and C2, and it need to intersect with C2. So the line that connect between C1 and C2 is this line. The mutual perpendicular is this line. And when it intersect with C2, at this position, it's gonna be the origin of the frame 2. How about the x2? X2 is the mutual perpendicular between C1 and C2. The mutual perpendicular between the C1 and the C2 is along this direction. So this is the direction of the x2. The relationship between x1 and x2 and x2 to x3 is similar, but for the frame 3, it's not a joint, but it's just an end effector. We put the frame on the end effector so that when we relate the origin of the end effector frame, we can describe the position with respect to the global frame. So for the end frame or the final frame or the end effector frame, actually you have two possible ways to define the direction. If you're gonna put a gripper on the end frame, on the end effector frame, maybe you may prefer the Z axis of the end frame to point outward from the robot. If you have a gripper, like here, maybe you're gonna point Z of the end frame outward and have the X of the end frame in the direction of motion of the gripper. But this is one possible choice. Another choice is make it easy. Just use the Z of the end effector frame to be in the same direction of the link before it, in order that when we compute the link twist or the angle between the axes, it still be 0 in the metric. So for the final frame, you have two possible ways to do it. The first way is to point the Z axis outward from the gripper direction and have the X axis in the direction of motion of the gripper. The gripper move out and in, right? The X direction can be here. Or the second possible choice, just put the Z axis with the same, with this. It's also possible. So in this step, we know how to attach frame. The next step is to obtain the parameter of each link, the DH parameter. The DH parameter A is the link length, alpha is the link twist, D is the link offset, and the theta is the joint angle. by definition, the link length is the distance between z I minus 1 and zi along the xi axis. The distance between the I minus the distance between the ci minus 1 and ci along xi. This is the link length. So the distance between z0 and zi along xi axis, xi is point into this direction. So the distance will be the radius of the cylinder here. So the link length of the first link will be r. How about the link to width? The link to width will be the direction measured from the ci minus 1 to the direction of the ci about the xi axis. By use the right hand rule, we begin with the z0 and then measure to the z1 and measure about the xi axis. The angle that we get here, is the alpha 1, and alpha 1 is equal to 90 degree. The offset is the distance measured from the origin to the axis xi along the zi minus 1 axis. So the offset of the link 1 is the distance measured from O0 to the x1 along the z0 the distance from O0 to x1 along the z0. As I mentioned, if we put O0 in the same level at the joint axis z1 at the same level with x1 or z1, if we put it on the same level, when we measure along the z0 axis, we can get the zero offset. But if we put O0 somewhere here, and we know that x1 is point into this level, if we need to compute the offset here, it will not be zero if you put the O0 somewhere different from here. So this is the link offset. The final one is the joint angle. Joint angle is the direction difference between the xi minus 1 to xi about the ci minus 1. The joint angle is the angle difference between xi minus 1 and xi about the axis ci minus 1. So for the angle 1 is the angle between x0 and x1 about z0. What is the angle between the x0 and x1 about z0 x0 and x1 about z0. Let's see this again, this picture. In the beginning, before the robot rotate, it may point the arm to this direction, But when it rotates with the angle theta 1, it changes the direction. Of the x1 away from the direction of the x0 with the theta that is driven by actuator. So direction measured from x0 to x1 about the z0 axis is the joint angle of the joint 1. So in this case, the joint angle will be theta 1. I put the star here. The meaning is this is the joint angle. No, this is the joint variable. Joint variable means you can use actuator to drive this angle. You can drive this joint by a motor to change the angle. And it's a joint variable. The other parameter, the radius, is fixed. You cannot change it. It's the parameter of the robot design. The link twist, 90 degrees, to change from the vertical direction to the Z1 direction. It's 90 degrees. It's never changed. It's the robot design. The offset, if you already set the origin, the offset will be the value that corresponds to the place that you set the origin. But it cannot be changed during the motion of the robot. So its parameter is not the joint variable. So no star on that parameter. Okay, for the DH parameter of the link 2, DH parameter of the link 2, the link length is the distance between the Zi minus 1 to the Zi along xi. So the link length of the link 2 is the distance from Z1 to Z2 along x2. C1 to C2 along the direction of x2. So the distance will be L1. The link width, the angle from C1 to C2 about x2, the angle difference between C1 and C2 about the axis x2, the C1 and C2 has the same direction. So the link to it is 0. The offset is the distance between the origin and the x-axis along the z I-1. So the offset of the link tool will be the distance between O1 to X2 along C1. D2 is the distance between O1 and X2 along C1. O1 is here and X2 is on the same level. I mean, O1 is this point. The X2 is lie on O1. I mean, O1 and X2 is intersect. It means O1 is on the line of the X2. So when we measure the distance along the C1, the offset will be 0. But in some robot, if the X2, instead of having the link here, if some robot has the link there, has the link to there instead, maybe we gonna have the value for the D2, because when we measure the X2 to the O1, we can have this distance, and this distance may be the D2. But in our case, the D2 also 0. How about the joint angle? The joint angle theta 2 is the angle between x1 and x2. Theta 2 is angle between x1 and x2 about C1. The angle between the x1 and x2 the angle between x1 and x2 measure about the C1, measure about this. Is this angle, is theta 2. And again, we put the star here, which indicate that we can drive the the theta 2 by a motor to create an angle. For the link tree, you will check by yourself, but as I mentioned, the relationship between the link, the frame 3 and frame 2, and the relationship between the frame 1 and frame 2 are the same. So if you see in the table, we have the same pattern of the parameter for this link. But if you try to put different arrangement of the frame 3, if you put the C3 in this direction, for example, you may have the different parameter here. Okay, we're gonna break for 10 minutes. For 15 minutes is fine. We will begin again from 3:10. But until now, what we get is we know how to attach frame, and we know how to obtain the DH parameter for each link, but we still don't know what is the benefit of computing this complicated parameter. How can we use it? So after the break, we will know how can we use the parameter, DH parameter, to obtain the forward kinematic of the robot. โอเคเบรกครับ
เบรกถึงกี่โมงนะครับ
เบรกถึง3:10 ครับ
โอเคครับ